Now let's do some actual thermodynamics problem using the first law of thermodynamics. So here's the first one. So it says 0.004 mole of gas undergoes the isothermal process. Isothermal process means constant temperature process shown in the diagram. So the gas undergoes expands from its initial state to final state following this hyperbola. But temperature remains constant during this process. That's what the isothermal change means. So in practically, how do you do this kind of change? You need a gas cylinder fitted with some piston, as explained in my lecture slide, and then you fill a number of moles, and then so then this gas expands, right? When you apply some heat, the gas expands, and this drives the piston and does some work, and then these are the questions. So that's how it works in reality, and this is basically used in heat engines actually, which we will very briefly mention that. So okay, so here's the first question. What are the initial and final temperatures? Right, initial and final temperature. So, and we obviously know initial and final temperatures must be same because it's an isothermal change. So first question is, what's the initial and final temperature? So then using again PV is nRT, so this is our main equation. So to find the temperature, what do you need? So we are finding the initial temperature, so you need initial states, right? Initial pressure, initial volume divided by n times r. N times r remains constant. Only pressure and volume will change here. So initial pressure. So if you look at the scale, the pressure is given in atmosphere. So whatever you have to multiply by 1.013 times the power fifth, because one atmosphere has that much pascals, right? And this is in centimeter cube. So meter, so centimeter cube. So whatever volume you have to multiply by 10 to the power minus 6 to convert into meter cube, because we want to do everything into standard units. Okay, first let's find the initial and final temperature. So initial pressure is 3 atmosphere, 3, but you have to convert into, like I said, into pascals, right? And initial volume is 100 centimeter cube, 100 centimeter cube, but we want in meter cube, so multiply by 1 millionth. And then n is the number of moles, which is given 0.004, and r is universal gas constant. Gas constant is always constant. Okay, so you can now solve for the initial temperature. Initial temperature is 914 Kelvin, right? And you don't have to solve for T final. T final is equal to T initial. Why? Because it says so. Because it says it's an isothermal change. This is an isothermal process. Temperature remains constant. So temperature here and temperature here remains constant. Okay, next question is, what's the final volume? Right? Because on this scale, as you can see, the final volume of the gas is not given. So what's the final volume? And again, you can use the same formula. So P final, V final is nR, T final, everything has to be final. So then we're solving for V final, right? nR T final divided by P final, right? So V final will be 0.004, 8.31. Temperature final temperature initial are equal, divided by P final is given is 1 atmosphere pressure. So 1 atmosphere is 1.013 10 to the power fifth. Okay. So then that should be your volume, and that's, if you calculate that, it's going to be 300 10 to the power negative 6 meter cube, or this is same as 300 centimeter cube. You can just keep it in meter cube. Or if you want to do quickly, you can just do Pi Vi over Ti is P final V final over T final, and T will cancel because it's isothermal change. Then you can find out the final volume quickly, right? So and then just plug the numbers. You can either do directly using the gas law, ideal gas equation, or just equation of state. Okay, next question is, what's the work done by the gas? Right? There's no two problems, it's just one problem. What's the work done by the gas during this process? So remember, this is the isothermal change, and work done by gas in any gas process in thermodynamic process is just the area under the curve, right? This work done is just the area, net area under the curve. But since it's curved, right, you can't really, unless it is straight line or flat line, you can't really find the actual area, right? So you have to do some calculus. So that's why we have the formula. If it is isothermal change, we have the formula. Okay, so if you are given isothermal change, you get hyperpolar, right? Initial state, final state, and we know that it's the area under the curve. But how do you find the area under the curve? You need to do some integration. You need to do some calculus. So and then the formula will be given, and this formula is only for isothermal or constant temperature process. If this is a straight line, triangle, something like that, you have to find the area under the curve. So the area under the curve is given by this equation, nRT log final volume divided by initial volume. That's how you find the work done during isothermal change. Okay, now let's plug all the numbers. Is 0.004 is the number of moles, R is 8.31. So since temperature remains constant, so initial and final temperatures are constant, so I use one of these. So both are 914. And then natural log, this is natural, volume is 300 divided by final volume is 300, initial volume is 100. And right, you can just keep in centimeter cube here because both will cancel out anyway. Okay, this is natural log 3, and if you do that, so you get 33.4 joules positive, because the work done could be positive or negative. Okay, so the gas does that much amount of work during this process. Alright, so similar question. Again, thermodynamics. It says the gas in a cylinder, right, undergoes expansion, gas expands from initial state A to final state B, but it follows in this time it follows a straight line like this, you're given the scales. So pressure is in kilopascals, so volume is in centimeter cube, so you have to multiply -6 meter cube. So you have to, this is times 1000, right, in pascals. So then three questions. So what are the initial and final temperature of the gas at state A and state B? And that's pretty straightforward. So just again use PV is nRT, right, using this basic equation. So temperature at A is given by pressure at A, volume at A divided by nR. So pressure at A is 100 kilopascal, so this is kilopascal multiplied by 1000. Volume at A is 200 centimeter cube, so -6 divided by number of moles 0.8 10 to the power -3, and R is 8.31. So if you do this calculation, so you're gonna find that it's 301 Kelvin. And similarly, temperature at B is, now you need pressure at B, volume at B divided by nR is same. So pressure at B is 400 kilopascal. Volume is 300 centimeter cube, -6 divided by, this is going to be same, N and R. And again, if you do this calculation, the temperature is going to be 1805. Double check that. Okay, this is the first answer. So this is the temperature of the given gas at state A and B. So the next question is, how much work is done by the gas during this expansion? Okay. So again, in general, for any thermodynamic process, the work done by gas during this process is just the area under the curve. This whole area, you need the whole area, right? So whole area under the curve. And this is made, now you can split into two. So area of a triangle, let's say area 1, and area of a rectangle, A2. So our general rule, since this is a triangle, right? It's a straight line triangle, so you can just use the area. So the net work done in general in any thermodynamic process is just the net area under the curve. right? If the curve is hyperbola, then you have to use the equations for isothermal chains. Okay, net area is A1 plus A2 as shown in the diagram. So area A1 is the area for triangle, which is 1/2 base times height. So base is 300 minus, the base is 300 minus 200, 100, 10 to the power negative 6, right? The height is 400 minus 100, so 300 kilopascal. It's kilopascals, right? Plus second area is just the area for triangle, which is the length times width. So length is 300 minus 200, 100. Again, this is negative 6 because it has to be in centimeter cubic meter, and the height is just the 100, but since it is in kilopascals, 10 to the power 3. So that's the total area, which must be the net work done during this process. And if you do that, it's going to be positive, because this work done could be both positive or negative. So since the gas expands, it's a positive work. So 25 joules if you check. Next question is how much heat is absorbed or exhausted by the gas. Okay, at Q. So how do you find the Q? Q is the heat exchange, heat added or exhausted by the gas. And then you have to use the first law of thermodynamics. Remember, first law of thermodynamics, it says the heat added to the system of gas is always equal to the change in thermal energy, internal energy, delta U, plus work done by the gas, right? So this is called a very important law in thermodynamics. It's the first law of thermodynamics. So you're going to need two things to calculate Q. You want a change in thermal energy, which we can calculate. We got the formula. W we already know. Okay, so change in internal energy or thermal energy is the U final minus U initial, plus this is 25 joules. So how do you find U final and U? So U, and if you check the formula, the thermal energy or internal energy of any gas, 3/2 nRT. Okay. So 3/2 nR, so final is the state B, so you need temperature at B, minus 3/2 nR, initial temperature is temperature at A, which we already know. So that's it. And then just put all the numbers. 3/2 N is A 10 to the power negative 3, and R is 8.31. So this is common factor, so TB minus TA. So temperature at B is 1805 minus temperature at A is 301 plus 25 joules. So if you do all this calculation, so it's going to give you again positive 175 joules. Again, remember, this heat Q could be positive or negative. So here it just happened to be positive. Positive simply means heat is positive, obviously means heat is added to the gas, to the system means system of gas. Okay, so that's how you calculate thermodynamics problem. So I'm going to solve one more problem on thermodynamics. So here's unlike before, it's a cyclic process, so it's not just one step. So say the gas in a cylinder, right? The gas, again, in practically is actually the application. This application is in heat engines and refrigerator. So certain gas is enclosed in a cylinder, and gas expands. And gas is compressed and expands. And it forms a cyclic process. So similarly, the gas, it says first it goes from state 1 to state 2, and then from 2 to 3, and the gas is again compressed from 3 to 4, and then finally back to the original state. And during this process, it's asking how much total heat is absorbed, how much total heat is emitted, right? But to do that, this long problem, I'm just gonna ask you a simple problem. Okay. So we are just solving, let's say, I'm just picking some random. So what's the heat exchanged by the gas during 2 to 3? And I will add one more. What's the total heat exchange during 3 to 4? Okay, so these only this. We'll be solving only these two problems, and which is similar to one of your homework problem. Okay, so then again, remember to find the Q, which is the total heat exchanged. What do you need? You need these two quantities from first law of thermodynamics. You need a change in thermal energy, and you need the work done. So change in thermal energy is 3/2 nR, right? Because this is common factor. Final temperature minus initial temperature. That's the change in thermal energy plus double. So okay, we're gonna need all these quantities. We're gonna need temperature at each state, and we're gonna need the work done, right, for each state. So that's all. And you can make a nice table if you want to solve it systematically. And this kind of, like I said, closed system, cyclic process is used in a heat engine, actually, operation of heat engine. This is the cylinder. Okay, so first we're going to need temperature at 2, 3, and 4. So first find temperature at 2 is pressure at 2, volume at 2 divided by nR, right? So this is again in centimeter cube, so you have to multiply by -6 cube. This is in atmosphere, so you have to multiply this by 1.013 to the power 5th, because we want in pascals, conversion factors. So pressure P2, so at 2 the pressure is 8 atmosphere, so 8, but you have to convert into pascals. Volume at 2 is 400 centimeter cube, so 400 10 to the power -6 divided by number of moles is given 0.04, and R is always constant. Okay, so first find the temperature at 2, and the temperature at 2 will be if you do that, 975 Kelvin. Similarly, we're going to need temperature at 3, be 3 over nR, and P at 3 is 1.013 10 to the power 5th. Volume at 3 is 500 10 to the power -6 divided by 0.04, 8.31, and 3 is 762 degree Kelvin. You need one more, temperature at 4. Temperature at 4 is P4 V4 divided by nR. Pressure at 4 is 5 5 atmospheric pressure, 113 10 to the power 5 pascals. And volume at state 4 is 100 centimeter cube, right, divided by, okay, so temperature at 4 is going to 152 Kelvin. Okay, so after finding temperature, why we're finding temperature? Because we need those here. And you need one more thing. You have to now first so to use this formula, so we already got the temperatures, which is good, but we also need to find the work done during each process. So first let's find during the process 2 to 3. So what's the work done? Work done is again net area, right, under the curve. So what will be the net area? So net area is, so from the given diagram, net means it's not just the triangle here, it's the whole area under the curve. Okay, it's just net area under the line or curve. That's going to give you the, and this is again the area. Let's divide into A1 and A2, right? It's the area A1, which is triangle area, rectangle area. So just like before. So this is the area or work done during 2-3 process. So which is A1 plus A2. So 1/2 height times base. Height is 8 minus 5, 3 atmospheric pressure. So 1.013 times the power 5 pascals. That's the height, right? Height is 8 minus 5. This is the height, is 3. And the base is this. So 500 minus 400. So 100. But it's in centimeter cube. So that's the area A1. Plus you have to add one more area because it's the whole area you need, right? So this, the area for rectangle is easy, so it's base times height. So base is 500 minus 400, so 100 10 to the power -6 times height, which is the pressure. So this is 5 atmospheric pressure. So 5 into again 1.013 10 to the power fifth. Okay, so that's gonna give you W23 process, and that's gonna give you so calculate that. This if you okay, so calculate that. I will leave it to you. It's just the numbers now. The second part is A2, right? So then we're ready to find Q, the heat exchanged. Okay, so once you do that, then we're ready to find our back to the main problem. Q 2 to 3 is delta U plus W, right? So delta U is 3/2 NR temperature at, so it's final, right? So you need the final temperature. Final temperature is 3, initial temperature is 2 for 2-3 process, right? So temperature at 3 minus temperature at 2, which we already know, and area is W23 from the previous part, right? And so calculate that. So 3/2 N is number of moles, 0.04, 8.31. Temperature at 3 is 762 minus temperature at 2 is 975. Okay, so the change in thermal energy is negative actually, right? Because this is bigger. Plus work done 3, which is from here. So, and do this calculation, right? Put all the numbers, and then you will end up with this. So I have the final answer as negative 40 joules. Okay, so you can clearly see, right, the heat exchange during 2-3 came out negative. So what does it mean? So negative simply means is the gas exhaust heat is subtracted from the system, right? Is the gas exhaust, the heat is removed. In other words, heat is negative means, right, removed from the system of gas. That's the meaning of negative. Okay, so and it's asking, so I'm asking you one more thing, right? Q34 process. So again you need delta U plus W, which means delta 3/2 NR. So you're going from 3 to 4. Your final state is 4, right? So temperature at 4 minus temperature at 3. Plus work done is work done during 3-4, and which is a compression. It's a negative work. So compression from the given diagram, right? It's a negative work. Okay, you have to make it negative. The area, you have to make it negative because the gas is compressed during this process. So because since you are going backward, it's a negative area. Okay, so 3/2 N is this. Temperature at 4 is 152 Kelvin, and temperature at 3 is 762 Kelvin, right? Plus work done during 3-4 process, again back to the, is now just the compression negative area, or the area of this rectangle, which is this, which is 5 atmosphere times 400, right? It's just the area of a rectangle. So it's going to be it's going to be just the height is the 1.013 10 to the power fifth. That's the height, times width is 500 minus 1 is 400 10 to the power negative 6. So that's going to give you Q34. So the heat excess during 3 to 4, when gas is compressed from 3 to 4, is going to give you this. And this is, if you do this calculation, you will find that out. Where is the Okay, you can do this calculation, and again it could be negative, yeah, and it could be positive actually. It could be negative, it could be positive. Okay, so just to let you know, so this is the main idea, first law of thermodynamics. To calculate the heat exchange, right, in any thermodynamic process, you need two things: the change in thermal energy or internal energy, which is given by this, plus the work done, and work done is in general area under the curve.